You know, every single day, we live inside this invisible fortress. It's what protects our emails, our bank accounts, our private messages, everything. And for decades, we've believed this fortress, built on digital encryption, was just unbreakable. But what if I told you the key to blowing the doors wide open has already been made?
Yeah, get a load of this. When the now famous RSA encryption came out back in '77, this was the promise. Not just a tough lock, but one that would take 40 quadrillion years to pick. I mean, that's not just secure, that's practically infinite. We're talking a truly unbreakable code.
So how in the world did this quote-unquote perfect lock actually work? You know, what was the secret sauce that made everyone so confident?
Well, the absolute genius of RSA is how it uses something pretty simple: prime numbers. Think of it like this. You have a public key, a huge number we'll call n, that anyone can use to lock up a message in a box. But the only way to unlock that box is with the private key. And that private key is the two secret prime numbers, p and q, that you multiplied together to get n in the first place. See, multiplying p and q is super easy for a computer. But trying to work backwards, to take that huge number n and figure out which two primes made it, that is an incredibly, monumentally difficult task. That one-way street is literally the bedrock of our entire digital world.
But you know how it goes. Where there's a lock, there's always someone trying to pick it. That word, impossible, well, to a codebreaker, that's just an invitation. And so began this relentless race to see if the impossible could, in fact, be done. So much for 40 quadrillion years, right? That big promise? It didn't really hold up. By 1994, a key that was supposed to be impossible was cracked in just 17 years. Then, in 2009, an even bigger, tougher one was broken. With every new generation of computers and, just smarter ways of doing things, that once impossible task was starting to look very, very possible. The walls of the fortress were definitely getting thinner. And the weapon they were using was something called the number field sieve. Basically, it's a two-step brute force attack. First, you get thousands of computers all working together, scanning for numbers with very specific properties. Then, you take all that data and feed it to a massive supercomputer that crunches it all to find the final secret keys. It's powerful, for sure, but it's still kind of like chipping away at a fortress with a hammer. But a new kind of threat was coming, one that wouldn't need a hammer, because it could just walk right through the walls. Okay, so now we're going to step into the really weird and amazing world of quantum computing. This is a place where all the rules we know about information just get tossed right out the window. So your laptop, my phone, they run on classical bits. And a bit is simple. It's either a 0 or it's a 1. It's on or it's off. But a quantum bit, or a qubit, well, think of it like a spinning coin. It's not just heads or tails. While it's spinning, it can be heads, tails, or kind of both at the same time.
And this both at the same time thing is a property called superposition. And this is the crucial part. Because a qubit can hold multiple values at once, a quantum computer can explore millions of possibilities simultaneously. Instead of walking down a maze one path at a time, it's like it can check every single path all at once.
And then there's entanglement. Einstein called it spooky action at a distance, which is just a fantastic name. Imagine you have two of those spinning coins and they're magically linked. The second you stop one and see that it's heads, you instantly know the other one, no matter how far away it is also heads. It's this bizarre, secret connection that quantum computers can use to their advantage.
And this right here, this is where it all becomes terrifyingly real. There's a quantum algorithm called Shor's algorithm that is perfectly designed to solve the exact math problem that makes RSA encryption work. So a problem that would take the best supercomputer we have today billions of years to solve. A quantum computer could do it in a matter of seconds.
Just think about the implications of that for a second. Government secrets, the entire global financial system, all of our private data, everything we've locked away behind that so-called unbreakable code would be completely exposed. Just overnight, the fortress would just crumble. But here's where the story gets really cool. What if those same bizarre quantum rules that create this massive threat could also be the key to building a new, much stronger kind of security? And that's the whole idea behind something called quantum key distribution, or QKD. It's a way of sharing a secret key where the very act of someone trying to listen in is instantly detected. Not because of a clever piece of software, but because the fundamental laws of physics themselves are your security guard.
It's brilliant, really. Here's how it works. Alice sends Bob a secret key, but she encodes it in the quantum states of tiny particles of light,
photons. Now, if an eavesdropper, we'll call her Eve, tries to intercept those photons to read the key, the very act of her measuring them changes them. She can't help it. It's a law of quantum mechanics. So when Alice and Bob check a small sample of their key, they'll see errors that shouldn't be there, and they'll know someone's on the line. It's the perfect burglar alarm. You literally cannot look at the key without breaking a window and setting off all the bells and whistles.
But you know, this whole quantum revolution is about so much more than just building better locks. It's about completely changing how our machines think and how they see the world.
Right. As Dr. Yogesh Malhotra points out here, the ultimate goal isn't just to make a faster calculator. The real dream is to build a machine that can actually mirror the flexible, interpretive power of the human mind.
Think about it. Our computers today live in a black and white world. Their logic is binary. It's yes or no, 1 or 0. It's totally rigid. But quantum computing works in the gray areas. Its logic can handle yes, no, and maybe, all at the same time. It's a way of thinking that deals in probabilities and interpretation, which, when you think about it, is a lot closer to how we make sense of the world.
So I'll leave you with this question. We're standing on the edge of a new era. An era where computers might not just be about finding the single right answer from a list, but about understanding context, ambiguity, and nuance. So the real question for all of us is, what happens to our world when our machines stop just calculating and actually start making meaning?